Now, once we understood how the heat transfer takes place, so we have the several, basically three modes: conduction, convection and radiation. And again the delta T comes into the picture. And these all the three modes can be easily replicated using the electrical analogy of voltage and current. Any good book you can find out this analogy. Now, once we know how the heat transfer happens, then we would certainly like to know what are the modes of the thermal management, battery thermal management. And when we say the battery thermal management, modes of the battery thermal management, it basically can be divided into two categories: active and the second one is passive. When we say active, basically it takes energy, or it takes energy from the pack itself to run its, to manage the heat. There are several ways to do that, to achieve. The simplest one is the air cooling system or air thermal management system. In that, we simply blow air. We suck the air from the ambient and throw over the battery, and it takes away the heat of the battery. There are several designs available for that one, and one can come out with their own unique design for the most efficient thermal management system using the air cooling system. What is the problem with that? You cannot go below the ambient temperature. But if you see our thermal, when we say where the cells work best is 15 to 35 degrees centigrade, and most of the time places like India, we have temperature beyond this, and then there is a heat generation inside. And which you have to take out. When such things happen, the air cooling or thermal management using ambient air would not be the best. However, the energy consumption is very, very low. You just have to run a fan or a blower. Now, the second important thermal management system, active thermal management system, is liquid cooling system, widely used in IC engine vehicle for the engine thermal management system. The efficiency is much higher than the air cooling system, but again you cannot bring down the temperature below ambient. If you wanted to keep your circulating medium intact, in the sense not consumable, in that case you cannot bring down the temperature much below the ambient, because finally the heat has to be rejected to the ambient. However, the efficiency is much better than the air cooling system. So, whenever we wanted to have thermal management system which works, where my component works or system works above ambient, this is one of the best system, liquid cooling system. Now, if we have to bring down the temperature below ambient, the only options left is using something which can change its phase. can reject heat at the higher temperature and absorb the heat at lower temperature, and such things comes as a refrigerant using a medium known as refrigerant, compressors, etc. And that we say direct expansion refrigerant system, where it absorbs the heat from the battery pack and throws out to the ambient by virtue of changing its phase, pressure and temperature. But most of the places it becomes difficult to use only the refrigerant system. So, we use combination of either refrigerant and air system or refrigerant and liquid cooling system, and when we do such things, then it becomes hybrid system. In the hybrid system, one side is always refrigerant, other side it could be air or liquid. Similar things can also be done using a phase change material like water, but the problem is that it will go into the ambient, it would be consumed. If you do not want to consume, then you have to use something like hybrid system, where the one medium would be refrigerant, other medium would be either air or liquid. In all these cases, you consume energy, and that energy comes from the battery pack itself. However, it becomes important because you need to keep the battery pack between 15 to 35 degrees centigrade for your best of life, and in such cases the cost can be justified. Not only the cost, your battery pack also has to be of moderately large capacity. In very small battery packs, you do not have that much of energy which can run something like direct expansion refrigerant type or hybrid system. Maybe air cooling is possible because of the very low energy demand, but again not for a very small battery pack. So, you should have a sufficient energy available in the battery pack. That means battery pack should be sufficiently large to utilize active cooling system. When your battery pack is small, what should you do? When your battery pack is small, in such cases the passive cooling system, which does not draw any energy from the battery pack, is mostly used. So, what becomes your goal at that time? Your goal is your temperature should not exceed much. You cannot control the temperature much, but then what you try to do, that my ambient is at 35 degree, in that case my battery pack should not go more than 35 degree or 36 degree or 37 degree or 40 degree. If it goes 50 degree, what happens? Your cycle life comes down. You do not want cycle life to be compromised much. You compromise, but as minimum as possible. Instead of 3000 cycle, it gives you 2800 or 2700, not 800 or 700. So, in such cases passive thermal management system works well, especially for a small battery pack, it works well. What are the passive thermal management system? One of the most widely used the passive thermal management system is use of phase change material. When I say phase change material, obviously you have to look a lot of things there, mostly the ambient condition. Now, if my ambient is going up to 45 degree, places like Chennai, that's happened. So, I will use a phase change material which works, which changes phase around at 45 degree centigrade. Because if I use anything less than that, let us suppose I use a 30 degree phase change material, that will work great for the battery pack, but will not be charged. Again, charge and discharge I am using here is charging is a solidification and discharging is liquidification of phase change material, or if it is liquid to gas phase change material, accordingly it works. So, if you are using a 30 degree phase change material at an ambient of 40 degree, what happens? It would already be in melted form, it cannot take further heat, So one has to worry about what could be the ambient condition if they are using this phase change material. The another one is embedded micro channels. In this, what happens, because of the capillary actions, the first of all, the fin density is very high, so that helps to release the heat into the ambient. The second is, if we combine with something like heat pipes or thermosiphons or such things, that helps by phase change, again by phase change, but at much lower cost, by capillary action or thermosiphon actions, to manage the heat properly. So it takes heat from the battery pack, releases into the ambient. It's in much efficient way. Obviously, we have to worry about weight, and that same thing is also with the phase change material. But then the good thing about this thing is that it does not take any energy from the battery pack. And our aim is also not to always maintain 15 to 35 degrees centigrade. What our aim is that to maximize the life by restricting the temperature rise as minimum as possible. So with that, we have discussed here various modes of thermal management system, both for large packs and small packs, and based upon the requirement we select either active or passive, and we select once, then we start designing that. First we try to get that heat load condition, and based upon the heat load condition we calculate all other things together, and then we design. So active thermal management, forced air convection, this can be enhanced by increasing the fin surfaces, and that would ultimately increase the heat flux which can be taken out. It's good up to 0.5 watt per centimeter square. It works well. Now the second is the liquid cooling of a battery pack. It has very high heat rejection. Heat flux it can handle is 0.5 watt to 2 watt per centimeter square. Then it comes immersion cooling. It can take very high heat flux because your whole pack is immersed in a liquid, and the the good thing about this immersion cooling is that it can penetrate even the intricate places. So it can minimize the hot spot formation, and mostly it is being used nowadays in data centers. A lot of data centers, lot of static electronic components, because when you are filling with some liquid, the weight increases. So you don't do that on the regular battery pack, but yes, if I have a lightweight material, we can try to utilize that. Again, this heat has to be rejected to the ambient, so you need to have a proper design which can reject the heat to ambient. It can also utilize the phase change by boiling and condensation, and similar to the direct expansion type of refrigeration cooling. But then a system has to design which can reject the heat outside. These liquids are generally have very high dielectric strength, so there would not be any electrical conductivity. You cannot use simply water because it has a high electrical conductivity. We use a material which does not has electrical conductivity, very high dielectric strength. The another way of localized cooling is using the Peltier device or Peltier cooling. Problem with that is it can take up to 6 watt per centimeter square. The temperature less than 0 degree centigrade is possible to achieve, but the cost wise as well as efficiency wise, the cost is very high, efficiency is very low. And whenever we say thermal management system, generally something we also understand coefficient of performance. For these systems, the coefficient of performance comes approximately 1. For this, the coefficient of performance could be as low as 0.5. for the cooling application. For heating application, it could be as good as 2. How do you select a thermal management method? What we were talking in the last slide, that if we are able to calculate, or if we are able to understand what could be the heat flux which we need to remove, and heat flux is nothing but heat generation by surface area, that is what is the heat flux, Q by A. Heat generation by surface area, and when we say surface area, from the surface you wanted to take out the heat. So that becomes an important parameter in selecting a thermal management system. So once you know the heat flux, then based upon the heat flux you can select appropriate thermal management system. Like if you have up to 10 to the power minus 4 watt per centimeter square per Kelvin, that is heat transfer coefficient per degree Kelvin, you should utilize something known as natural convection, and that could be air mostly, up to 10 to the power minus 3 watt per centimeter square per Kelvin. Higher than that, you should start looking single phase forced convection like liquid cooling. When you are going up to 1 watt per centimeter square per Kelvin, then you have to start using the two phase boiling method, boiling and condensation method, and that is what exactly happens in the direct expansion refrigerant cooling or in a hybrid system. So let us do a problem on that example, selection of a thermal management method. So the same curve is here. So what it is saying, utilizing the result from the previous example, what was the previous example, 2P16S 80 degree C2, sorry 100% SOC2, 20% SOC at 1C discharge. Now our heat generation was 62.72 watt there, and what we have to do, we have to maintain the pack temperature at 45, ambient condition is 35 degrees C. So I cannot go beyond 45 degrees. This is what I have already set a limit, because this is what it can give me the best life. Even though for best life 15 to 35 degree centigrade is the best option, but yes, I cannot achieve that unless I have active cooling system, but that pack is very small, so I cannot go for active cooling system. So I try to restrict, my temperature should not go beyond some particular temperature. When I say some particular temperature, so then I select that particular temperature based upon the cell characterization, testing and other things. And what we have found out, that 45 degree ambient is good enough for me to get a good number of cycle life from the battery pack, and I want to maintain 45 or below. My ambient condition is 35 degree. If I do not maintain still, what can happen? My temperature will further shoot up more than 45, and then what I wanted to get from that cycle life, I may not be able to get. Now assume that the convective area is 0.168 meter square. So that means surface area has been given. From here you can take out the heat, that area has been given. Ambient is 35, pack temperature 45, the heat generation is 62.72 watt. So let us solve this. The thermal resistance RTH is delta T by Q. Now T cell is 45 degree, this is the limit, the maximum limit. T ambient 35 degree C, heat generated this one, delta T 10 degree centigrade. Thermal resistance from this formula we have got, because delta T we know, Q we know, so it is 0.16 K per watt. Now using the electrical analogy, T1 45 degree C, T2 35 degree C, and what you have, thermal resistance is 0.16 K per watt. Now, convective resistance is nothing but 1 by HA. So, what we have? Thermal resistance this, convective area this much, and convective heat transfer coefficient 0.0045 watt per centimeter square per Kelvin. So, when I say what is the convective heat transfer coefficient, that is what it will come here. So, that is around 0.0045, it falls somewhere here. Now, what are the options I have? What are the options I have? So, I can go to natural convection. I can go to the natural convection using fluorochemical liquids. When I say fluorochemical liquids, it's mostly, it has a very high dielectric strength, not electrically conductive. So, I can utilize that. I can also utilize water, but when I am utilizing the water, I have to make sure that it does not come direct contact of the electrical path. What else I can do? I can also go for single phase forced convection. If I go for single phase forced convection, the air cooling is sufficient. That means I have to either use a fan or blower and design in such a way that it is able to take out all the heats. Many of the time you may not be able to get the fluorochemical liquids, because when you are using this liquid, again you have to make a thermal management system, proper thermal management system, so that no leakage or something happens. However, in the air cooling system, when it is forced using a fan or blower, you do not have to worry much about the containment, because air you suck from ambient and throw it out to ambient. But with the fluorochemical liquids or water, you have to worry about both the things together. So, for simplicity, it is always good to have the forced air cooling system here, and that is what it is placed here. Now, similar network can be modeled using heat transfer through cell holder insulation also. So, what we have considered only here is this one, thermal resistance part and convective resistance. Now, it can be done with the multi-layer. Now, what we have done, only one layer here. Now, if there is insulation between the cells, that I can model as another resistance. If there is a separator or compression pad, that I can model with another layer. If there is external casing, that I can model with another layer in the series. If something is coming in the parallel, that we can utilize. So, what I am trying to say you, this graph what we are showing you here is, through this you can easily select what could be the best thermal management system for your system, and then from there you start designing your system, and there you may have multiple options. Then you have to look upon the option which is easy to work, which could have much more robust design than anything else. Okay, any question till now?